Right now, at this very moment, something is consuming the mass equivalent of one entire Earth every single day. It sits at the heart of a galaxy called Holmberg 15A, and it weighs as much as 40 billion of our suns. For decades, astronomers believed black holes had practical limits, that the universe imposed natural boundaries on how massive these gravitational monsters could become. They were wrong. The largest black hole ever discovered defies every expectation we had about what nature permits, and its existence forces us to rewrite fundamental assumptions about how galaxies form, how the universe evolved, and what might be lurking in the depths of space we haven't yet explored. When astronomers first detected this cosmic leviathan, they had to verify their calculations multiple times. The numbers seemed impossible. A black hole this massive shouldn't exist according to our models of how these objects grow. There it was in the data. An entity so enormous that our sun could orbit within it with room to spare for billions of other stars. The event horizon alone stretches farther than the orbit of Neptune, encompassing a region of space larger than our entire solar system many times over. Light itself, traveling at nearly 300,000 kilometers per second, would need more than 2 days to cross from one side of this gravitational boundary to the other. We've known about black holes for over a century in theory, and we've observed them for decades through their effects on surrounding matter. We've watched stars orbit invisible points in space, measured X-rays screaming from superheated gas spiraling toward oblivion, and recently captured the first direct image of a black hole's shadow. But nothing prepared the scientific community for what deeper surveys would reveal, hidden in the cores of ancient galaxies. Black holes exist that make the one in our own Milky Way look microscopic by comparison. These are not just larger versions of stellar black holes formed from dying stars. They represent something else entirely, objects that challenge our understanding of physics, time, and the structure of the cosmos itself. Tonight, we're embarking on a journey to understand the largest black hole ever discovered. We'll explore how astronomers found something invisible that sits billions of light years away. We'll examine what happens at the edge of an object so massive that physics breaks down in ways that still confuse the brightest minds in science. And we'll confront what this discovery means for our place in a universe capable of creating monsters that dwarf anything in our everyday experience. 3 revelations await you in this exploration. First, the largest black holes didn't form the way we thought they did, and their existence points to mysterious processes in the early universe that operated under different rules than what we see today. Second, there's a cosmic competition happening between black holes and galaxies themselves, a feedback mechanism that determines whether a galaxy lives or dies. And the largest black holes sit at the center of this existential battle. Third, we may have already found the largest black hole that can possibly exist, a maximum size imposed not by lack of food but by the fundamental structure of spacetime itself. Before we begin, if you're fascinated by the extreme objects hiding in the depths of space, subscribe and hit the thumbs up button. And here's a question to consider. If you could observe a supermassive black hole from a safe distance, what do you think you would actually see? Comment below with your answer. I'll pin the most creative response. The story of the largest black hole starts not with a discovery but with a prediction. Albert Einstein's equations suggested these objects might exist, but Einstein himself doubted nature would actually create them. Karl Schwarzschild calculated the exact boundary where gravity becomes inescapable while serving in the German army during World War I. Subrahmanyan Chandrasekhar proved that massive stars must collapse into something beyond comprehension. Robert Oppenheimer and his student Hartland Snyder published the first paper describing complete gravitational collapse in 1939, but for decades, black holes remained mathematical curiosities, solutions to equations that seemed too strange to represent physical reality. Then came quasars. In the 1960s, astronomers discovered objects that shone brighter than entire galaxies but appeared as single points of light. Nothing in known physics could explain them. The only mechanism capable of generating such enormous energy from such a small region was matter falling into a supermassive black hole, converting its mass into radiation with terrifying efficiency. Suddenly, black holes weren't just theoretical anymore. They were real. They were enormous. and they sat at the centers of the most powerful objects in the universe. The race began to find the largest one. Every new generation of telescopes pushed deeper into space and further back in time. Each survey revealed black holes more massive than the last. Astronomers kept raising their estimates of the maximum possible size. And then they found something that seemed to represent the upper limit. A black hole so immense that adding more mass might tear apart the very structure of the surrounding galaxy. Now let's begin our journey into the heart of darkness itself, where gravity becomes absolute and space and time exchange their properties. We start with a fundamental question that seems simple but opens doorways to the strangest realm in physics. Ultimate scale understanding the largest black hole requires first grasping what we mean by size when discussing an object from which nothing escapes. Black holes don't have surfaces in any conventional sense. The mass collapses to a point of infinite density called a singularity, at least according to general relativity, though quantum mechanics likely tells a different story at such extremes. What we measure as size is actually the event horizon, the boundary beyond which escape velocity exceeds the speed of light. For the largest black hole ever discovered, that boundary encloses a region of space almost unimaginable in scale. The current record holder, depending on measurement uncertainties and ongoing observations, is the black hole at the center of the galaxy Holmberg 15A. This ultramassive black hole weighs approximately 40 billion times the mass of our Sun. To put that in perspective, imagine taking every planet in our solar system, every asteroid, every comet, every speck of dust, gathering all of it together, and then adding the Sun itself. Now multiply that total mass by 40 billion. The number becomes abstract, but the implications are concrete. This single object contains more mass than many entire galaxy clusters combined. The event horizon radius for such a monster extends to roughly 690 astronomical units. One astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. Our solar system's most distant planet, Neptune, orbits at 30 astronomical units. Pluto's orbit reaches about 40 astronomical units at its farthest point. The event horizon of this black hole stretches more than 17 times farther than Pluto's orbit. If you place this black hole where our Sun sits, its gravitational boundary would extend past the orbit of Neptune and deep into the region we call the Kuiper belt, where icy objects drift in the frozen darkness at the solar system's edge. Light takes approximately 4 hours to travel from the Sun to Neptune. That same light, moving at its constant universal speed, would need more than 2 full days to travel from one side of this black hole's event horizon to the other. Think about that for a moment. Light can circle the Earth more than 7 times in 1 second. It can reach the Moon in just over 1 second. It crosses the distance to the Sun in about 8 minutes. Yet this black hole's event horizon is so vast that light would spend days crossing its diameter. Comparing supermassive black holes reveals a hierarchy that mirrors the structure of the universe itself. The black hole at the center of our Milky Way galaxy, called Sagittarius star, weighs about 4 million solar masses. That's enormous by any human standard, with an event horizon roughly 17 times the size of the Sun. But compared to the monster in Holmberg 15A, our galactic center black hole is a lightweight, outmassed by a factor of 10,000. The black hole in the galaxy M87, famously photographed by the Event Horizon Telescope in 2019, weighs about 6.5 billion solar masses. That's more than 1,500 times the mass of Sagittarius star, yet still dwarfed by Holmberg 15A's behemoth by a factor of more than 6. How do astronomers measure something that emits no light and sits billions of light years away? The techniques combine observational astronomy with sophisticated physics. Black holes reveal themselves through their gravitational effects on surrounding matter. Stars orbiting the galactic center move at speeds determined by the central mass. By measuring stellar velocities and orbital periods, astronomers can calculate the mass of the unseen object holding those stars in their paths. The orbital mechanics work the same way they do for planets around the Sun, following laws Johannes Kepler discovered for centuries ago and Isaac Newton explained with his theory of gravity. For extremely distant black holes, direct measurement of individual star orbits becomes impossible. Instead, astronomers measure the velocity dispersion of entire stellar populations, using spectroscopy to detect how much the light from stars is shifted by their motion. Higher velocities indicate stronger gravitational fields, which indicate more massive central objects. They also observe the motion of gas clouds and accretion disks, which spiral around black holes at different speeds depending on their distance from the center. Water masers, which are naturally occurring microwave lasers powered by molecular clouds, provide especially precise velocity measurements for some systems. The galaxy Holmberg 15e sits at the center of the Abell 85 galaxy cluster, about 700 million light-years from Earth. This is not a young galaxy where active black hole feeding creates brilliant quasars. Holmberg 15a is ancient, a giant elliptical galaxy that formed when the universe was younger and galaxy mergers were more common. The central black hole likely grew through the successive mergers of multiple smaller supermassive black holes, each brought together when their host galaxies collided and combined. This process takes billions of years as the merged galaxies settle into new configurations, and the central black holes spiral inward through a mechanism called dynamical friction. Dynamical friction works because a massive object moving through a sea of stars creates a gravitational wake, similar to how a ship creates a wake in water. Stars behind the moving black hole get pulled slightly forward, gaining energy, while the black hole itself loses momentum and spirals inward. Eventually, two supermassive black holes can merge, releasing tremendous energy in the form of gravitational waves that ripple through spacetime itself. The LIGO and Virgo gravitational wave detectors have observed mergers of stellar mass black holes. But supermassive black hole mergers require different detection methods because their gravitational waves oscillate at much lower frequencies. Future space-based detectors like LISA, the Laser Interferometer Space Antenna, will target these signals. Other candidates for the title of largest black hole include TUN 618, a quasar with an estimated mass of 66 billion solar masses, though this measurement carries substantial uncertainty. Phoenix, another ultramassive black hole, may weigh up to 100 billion solar masses according to some estimates. Though these extreme measurements remain controversial and require confirmation with better data. The difficulty lies in measuring such distant objects through indirect methods that depend on assumptions about how matter behaves in extreme gravitational fields. What makes a black hole large shifts depending on what property you measure. The Schwarzschild radius, which defines the event horizon, scales linearly with mass. Double the mass and you double the radius. This differs dramatically from normal objects, where doubling the mass usually produces a much smaller increase in size because matter resists compression. Black holes have no such resistance. All the mass exists at the central singularity, at least according to classical general relativity, and the event horizon simply marks the point where gravity's pull becomes inescapable. The volume enclosed by the event horizon scales as the cube of the mass. Meaning a black hole 40 billion times the Sun's mass has an internal volume 64,000 trillion times larger than a black hole with one solar mass. But this volume contains no matter in the normal sense. It's empty space that happens to be falling inward faster than light can climb out. Crossing the event horizon wouldn't feel like hitting a surface or passing through a barrier. An observer falling toward a supermassive black hole might not notice anything special at the moment of crossing, though they would be doomed to reach the singularity eventually with no possibility of escape or even sending a message to the outside universe. The surface gravity at the event horizon actually decreases as black holes get more massive. A stellar mass black hole of 10 solar masses has such intense tidal forces at its event horizon that any object would be torn apart, stretched vertically and compressed horizontally in a process astrophysicists call spaghettification. But the event horizon of a supermassive black hole is so far from the central singularity that tidal forces there are relatively gentle. An astronaut falling through the event horizon of the Holmberg 15a black hole would survive the crossing intact, though their fate would be sealed. They could still shine a flashlight and watch the beam illuminate objects near them. They would see their watches ticking normally. Only when looking outward toward the universe they left behind would they notice strangeness, as light from outside would appear increasingly blue-shifted and concentrated into a shrinking circle behind. Then, now we understand the scale of the largest black hole ever discovered. The next question becomes more challenging. How did nature build something so incomprehensibly massive? Ancient growth. The formation of supermassive black holes represents one of the deepest mysteries in modern astrophysics. The largest black holes shouldn't exist if they grew through the most obvious mechanism, slowly accumulating matter from their surroundings over billions of years. The problem lies in the rate at which black holes can grow. When matter falls toward a black hole, it heats up through friction and compression, emitting intense radiation. This radiation exerts outward pressure on surrounding matter, pushing away the very fuel the black hole needs to grow. The balance between gravitational attraction and radiation pressure creates a natural limit called the Eddington limit, named after British astrophysicist Arthur Eddington, who derived it in the 1920s. The Eddington limit depends on the black hole's mass. More massive black holes can pull harder with gravity, overcoming stronger radiation pressure, so they can accrete matter faster in absolute terms. But even accounting for this scaling, a black hole that started with 100 solar masses shortly after the Big Bang and fed continuously at the maximum Eddington rate for 13.8 billion years would only grow to about 5 billion solar masses by today. That's enormous, but still less than the monster in Holmberg 1.5a by a factor of 8. Something else must be happening. Astronomers observe quasars, which are actively feeding supermassive black holes, existing when the universe was less than 1 billion years old. The black holes powering these ancient quasars already weighed billions of solar masses. They formed and grew to tremendous size in just a fraction of the universe's current age. This timeline poses a serious challenge. Regular star formation produces stellar mass black holes of perhaps 10 to 100 solar masses when massive stars exhaust their nuclear fuel and collapse. Even if such a seed black hole formed very early and fed at the absolute maximum rate allowed by physics, it couldn't grow large enough fast enough to match what we observe. Several theoretical solutions attempt to resolve this tension. Direct collapse black holes represent one possibility. In the very early universe, under special conditions, a cloud of primordial gas might collapse directly into a massive black hole without forming stars first. This requires a gas cloud to avoid fragmenting into smaller pieces, which normally happens when the cloud cools and molecular hydrogen forms. Molecular hydrogen is an extremely efficient coolant, radiating away energy and allowing gas clouds to collapse into dense knots that become individual stars. But if intense ultraviolet radiation from nearby sources destroys the molecular hydrogen, the gas cloud stays hot and remains intact, potentially collapsing into a black hole of 10,000 to 100,000 solar masses in a single event. These intermediate mass seeds would have a significant head start on growth. A black hole beginning with 100,000 solar masses needs to grow by a much smaller factor to reach billions of solar masses. And the shortened timeline becomes plausible even with Eddington limited accretion. The challenge is determining whether the required conditions actually existed in the early universe. Recent simulations suggest that direct collapse might occur in special environments, particularly in the halos of dark matter that preceded galaxy formation. Another pathway involves dense stellar clusters. In the crowded cores of the first galaxies, stars might pack so tightly together that collisions become common. When massive stars collide, they merge into even larger stars. This runaway process could produce a supermassive star weighing thousands of solar masses, which would be unstable and quickly collapse into an intermediate mass black hole. This seed could then grow through both continued stellar collisions and gas accretion to become the supermassive black holes we observe. Primordial black holes represent a more exotic possibility. If quantum fluctuations in the extremely early universe created regions of slightly higher density, these regions might collapse directly into black holes when the universe was less than 1 second old. Depending on the specifics of these fluctuations, primordial black holes might form with a wide range of masses. While most theoretical models suggest primordial black holes would be quite small, some variations allow for larger masses that could seed supermassive black hole growth. The challenge here is that primordial black holes remain hypothetical, and no confirmed examples exist. The most massive black holes likely grew through a combination of mechanisms. Continuous gas accretion provides steady growth. Black hole mergers, occurring when galaxies collide and their central black holes eventually combine, provide sudden jumps in mass. Major galaxy mergers are common in the early universe when galaxies were smaller and closer together. Holmberg 15a sits at the center of a galaxy cluster, and its enormous central black hole probably grew through multiple merger events as smaller galaxies fell into the central giant over billions of years. Numerical simulations of galaxy formation now include sophisticated models of black hole growth and feedback. These simulations start with the conditions of the early universe and follow the evolution of dark matter, gas, stars, and black holes through cosmic time using the laws of physics. The most successful simulations can reproduce the observed properties of galaxies today, including the masses of their central black holes, but only when they include super-Eddington accretion during certain phases. Super-Eddington accretion means the black hole feeds faster than the classical limit suggests, possibly because the geometry of the accretion flow changes in ways that allow more matter to reach the event horizon despite intense radiation pressure. Observations support the possibility of super-Eddington growth. Some quasars appear to be accreting matter at several times the Eddington limit, based on measurements of their luminosity and inferred black hole masses. The mechanism might involve thick accretion disks where the disk's own gravity helps funnel matter inward, or it might involve chaotic accretion where gas arrives from random directions rather than settling into a neat disk. Random accretion would be less efficient at producing outward radiation pressure because the radiation could escape more easily through gaps in the flow. The growth of supermassive black holes doesn't happen in isolation from their host galaxies. Strong correlations exist between black hole mass and various properties of the surrounding galaxy. The Im-Sidmore relation connects black hole mass to the velocity dispersion of stars in the galactic bulge, the dense central region of old stars. More massive black holes sit in galaxies with faster-moving stars in their cores. The relation holds across 5 orders of magnitude in black hole mass, from millions to tens of billions of solar masses, suggesting a fundamental connection between black hole growth and galaxy evolution. This connection seems paradoxical at first. The black hole's gravitational influence extends only a few light-years, while the galactic bulge spans thousands of light-years. How does the black hole know about the larger galaxy, or vice versa? The answer involves feedback mechanisms where the black hole's feeding affects the entire galaxy. When a black hole accretes matter rapidly, it can launch powerful jets and winds that carry enormous energy outward. These outflows can heat or expel the gas throughout the galaxy, suppressing star formation and changing the galaxy's structure. The process creates a self-regulating cycle where the black hole grows until its feedback becomes strong enough to cut off its own fuel supply. In the largest elliptical galaxies, this feedback appears to have been extremely powerful. Holmberg 15a is a giant elliptical galaxy that probably formed through multiple mergers of smaller galaxies. Each merger would deliver gas to the central black hole, triggering episodes of rapid growth and powerful feedback. The accumulated energy from these episodes might have expelled most of the galaxy's remaining gas, effectively ending both star formation and further substantial black hole growth. What remains is an ancient, evolved system where the black hole has reached equilibrium with its surroundings. Evidence for past activity appears in the form of cavities and shock fronts in the hot gas surrounding giant elliptical galaxies. X-ray observations reveal bubbles blown out by jets from the central black hole, some stretching hundreds of thousands of light-years across. The energy required to create these structures is staggering, equivalent to tens of millions of supernovae. Only a supermassive black hole feeding on gas and converting some of that mass into outflowing energy can power such phenomena. The growth of the largest black holes might have followed a violent, episodic path rather than smooth accumulation. Periods of intense feeding following galaxy mergers would alternate with quiet periods after the feedback expelled or heated the available gas. Each cycle would add to the black hole's mass while also changing the host galaxy's structure. After many cycles spanning billions of years, the system reaches the configuration we observe today, an enormous black hole sitting dormant in an ancient galaxy. Having consumed most of the available fuel, Understanding how these monsters grew requires looking back to an earlier epoch of cosmic history when the universe was denser, galaxies were forming rapidly, and black holes were engaged in their most violent feeding. The story of their growth is intimately connected to the story of how the universe came to look the way it does today. Invisible detection. Finding the largest black hole poses a unique challenge in observational astronomy. Black holes emit no light themselves, and the largest ones often sit in galaxies where the surrounding gas has been depleted or expelled, eliminating the brilliant accretion disk radiation that makes active black holes visible as quasars. Detecting these dormant giants requires indirect methods that measure gravitational effects on stars and gas orbiting at large distances from the event horizon. The techniques astronomers develop to find and weigh supermassive black holes represent some of the most sophisticated applications of physics to observational problems. The foundational method involves measuring stellar velocities in galactic centers. Stars orbit the central black hole following the same basic physics that governs planetary orbits around the Sun. Kepler's third law relates the orbital period to the orbital radius and the central mass. By measuring how fast stars move and how far they are from the galactic center, astronomers can calculate the mass of the object those stars orbit. This technique works best for relatively nearby galaxies where individual stars can be resolved and tracked over time. The most precise application of this method occurred in our own Milky Way galaxy. Since the 1990s, astronomers at the European Southern Observatory and the University of California, Los Angeles, have tracked individual stars orbiting Sagittarius A, the radio source marking our galactic center. Using some of the world's largest telescopes equipped with adaptive optics to correct for atmospheric blurring, they measured the positions of stars over many years, mapping complete orbits for several objects. One star, designated S2 or SO2 depending on which team named it, completes an elliptical orbit in just 16 years. Approaching within 17 light hours of the central black hole at closest approach. The measured orbit pins down the central mass to about 4.1 million solar masses concentrated in a region smaller than Mercury's orbit around the Sun. Nothing except a black hole can pack that much mass into such a small volume. For more distant galaxies where individual stars cannot be resolved, astronomers use velocity dispersion measurements. Spectroscopy splits light into its component wavelengths, revealing dark absorption lines where elements in stellar atmospheres absorb specific wavelengths. When many stars move at different velocities, these absorption lines broaden because some stars are moving toward us and others away, creating Doppler shifts that spread the line across a range of wavelengths. The amount of broadening indicates the range of velocities, and larger velocity dispersions indicate stronger gravitational fields requiring more massive central objects. Gas dynamics provides another measurement technique: rotating disks of gas orbiting galactic centers emit radiation at specific wavelengths characteristic of particular molecules, water masers, which emit microwave radiation at a wavelength of 1.35 centimeters. Prove especially useful. These masers occur in dense molecular clouds and act as natural amplifiers of microwave radiation, creating bright spots that can be tracked with interferometric techniques. Very long baseline interferometry combines signals from radio telescopes separated by thousands of kilometers, achieving angular resolution sharp enough to measure the positions of maser spots orbiting supermassive black holes in distant galaxies. As the maser spots orbit, their velocities can be measured through Doppler shifts, and their positions can be tracked to map the rotation curve of the gas disk. The rotation curve directly reveals the enclosed mass as a function of radius. The galaxy in GC 4258 provided one of the most precise black hole mass measurements using water maser observations. Radio telescopes detected a thin disk of molecular gas orbiting the galactic center, with maser emission tracing the disk structure. The disk rotates according to Keplerian motion, where velocity decreases with distance from the center in a specific mathematical relationship. Measurements of the maser velocities and positions allowed astronomers to calculate a central mass of 39 million solar masses with remarkable precision, and certain by less than 1%. This measurement also confirmed that the mass concentrates in a region small enough that only a black hole can explain it. For the most massive black holes in distant galaxies, even velocity dispersion measurements become challenging because the gravitational sphere of influence, where the black hole's gravity dominates over the collective gravity of stars, can be smaller than the telescope's angular resolution. At distances of hundreds of millions of light-years, the region where the black hole measurably affects stellar motions might appear smaller than a single pixel in telescope images. Astronomers must use statistical techniques and model the expected distribution of stellar velocities to extract black hole mass estimates from the data. Holmberg 15A's central black hole was measured using stellar velocity dispersion observations combined with models of the galaxy's structure. The galaxy sits in the center of the Abell 85 cluster at a distance of about 700 million light-years. At this distance, the central region appears as an extended fuzzy patch in even the best ground-based images. Spectroscopic observations measured the average velocities of stars in regions at different distances from the galactic center. These velocity measurements, combined with observations of the galaxy's light distribution showing how stellar density changes with radius, constrain the central mass through dynamical modeling. Dynamical modeling creates computer simulations of the galaxy where stars move according to the combined gravitational potential of both the black hole and the distribution of stars and dark matter. The models vary the black hole mass and other parameters, generating predicted velocity dispersion profiles that can be compared to observations. By finding which combination of parameters best matches the observed data, astronomers determine the most likely black hole mass and estimate the uncertainty in that measurement. For Holmberg 15A, the models indicated a central black hole of roughly 40 billion solar masses, though the uncertainty range extends from about 30 billion to 50 billion solar masses depending on assumptions about the galaxy's structure. Independent confirmation of such extreme masses would strengthen confidence in these measurements. Gravitational lensing offers one alternative approach. When light from a background source passes near a massive object, the object's gravity bends the light's path, acting as a lens that can magnify or distort the background source's image. Supermassive black holes can gravitationally lens light from stars passing behind them, creating brief brightening events as the black hole's gravity focuses the starlight toward Earth. These micro-lensing events are extremely rare and difficult to observe, but future surveys monitoring millions of stars in distant galaxy centers might detect them. Providing independent mass measurements. Direct imaging of black hole shadows offers another approach. The Event Horizon Telescope collaboration achieved this for M87's black hole in 2019 and for Sagittarius A star in 2022, creating images showing a dark central region surrounded by a bright ring of emission from hot gas. The shadow's size is directly related to the black hole's mass and distance. For M87, located about 55 million light-years away, the shadow appeared about 40 microseconds across, matching predictions for a black hole of about 6.5 billion solar masses. Extending this technique to more distant or larger black holes requires improving the Event Horizon Telescope's sensitivity and possibly adding telescopes to the array. The uncertainty in black hole mass measurements increases with distance. Nearby black holes like Sagittarius A star can be weighed with precision better than 1%. At distances of tens of millions of light-years, precision drops to perhaps 20 or 30%. For the most distant supermassive black holes hundreds of millions or billions of light-years away, measurements might be uncertain by factors of 2 or 3. This uncertainty means competing claims for the title of largest black hole remain difficult to definitively resolve. Different studies using different techniques or different assumptions can produce significantly different mass estimates for the same object. Systematic uncertainties add further complications. Dynamical models assume stars and gas move in response to gravity alone, but magnetic fields, turbulence, or non-gravitational forces could affect the motion in ways the models don't capture. Distance measurements to galaxies carry their own uncertainties, and errors in distance directly translate to errors in inferred black hole mass. Selection effects bias samples toward black holes that are easier to detect, potentially missing extremely massive but dormant black holes that produce no bright radiation and sit in galaxies' worst. Large motions are difficult to measure. Despite these challenges, the overall picture remains consistent. The most massive galaxies host the most massive black holes. And the relationship between black hole mass and galaxy properties follows predictable patterns across a wide range of scales. Outliers exist where black holes seem overly massive or surprisingly small for their host galaxies' properties. And these outliers provide clues about different evolutionary paths galaxies might follow. But the general correlation, combined with measurements of individual systems using multiple independent techniques, gives astronomers confidence that ultramassive black holes like the one in Holmberg 1.5a truly exist. Advances in telescope technology promise better measurements in the coming years. The James Webb Space Telescope's infrared capabilities can peer through dust to reveal galactic centers more clearly. Upgraded ground-based telescopes with larger mirrors and improved adaptive optics will resolve smaller angular scales. Future extremely large telescopes with mirror diameters of 30 to 40 meters will push stellar orbit measurements to greater distances. And next-generation gravitational wave detectors will catch the mergers of supermassive black holes, providing direct confirmation of their masses through the gravitational wave signal analysis. The challenge of weighing invisible objects billions of light-years away showcases human ingenuity in applying physical laws to extract information from faint signals crossing vast cosmic distances. Now, we turn to what happens at the edge of these extreme objects, where gravity becomes so intense that reality itself transforms in disturbing ways. Event horizon. The event horizon represents more than a boundary in space. It marks the point where the nature of causality changes, where the future becomes completely disconnected from the outside universe, where time and space exchange their roles in ways that challenge intuition. For the largest black holes, this boundary encloses a region large enough to swallow our entire solar system, yet the physics operating there remains the same bizarre physics that governs all black holes regardless of size. Understanding what the event horizon means requires confronting ideas that seem impossible yet follow inevitably from the mathematics of general relativity. General relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Massive objects bend spacetime around them, and other objects follow the straightest possible paths through this curved geometry. Those paths appear curved from an external perspective, which we interpret as objects falling or orbiting under gravity's influence. Near a black hole, the curvature becomes so extreme that the geometry of spacetime fundamentally changes structure. The event horizon marks where this change becomes absolute. Outside the event horizon, an observer can maintain a constant position relative to the black hole by using thrust to counteract gravity's pull. Rockets or any force can hold a spacecraft steady, though the required force increases as the spacecraft approaches the event horizon. Exactly at the event horizon, maintaining position would require accelerating at infinite force, which is impossible. Beyond this point, no amount of force can prevent falling inward. The future direction of all paths leads toward the singularity, and nothing can reverse this fate. This inevitability arises from the structure of spacetime itself inside the event horizon. Outside, time flows into the future and space extends in various directions that objects can move through. Inside the event horizon, the time-like direction that represented the future now points toward the singularity. Moving forward in time necessarily means moving toward the singularity, with the same inevitability that outside objects must move forward in time toward the future. Just as you cannot stop time from advancing outside the black hole, you cannot stop falling toward the singularity once inside. The direction toward the singularity has become the future itself. Event horizon light provides another way to understand the event horizon. Imagine shining a flashlight outward while falling toward a black hole. Outside the event horizon, the light travels away from the black hole at its constant speed, though observers at large distances would see the light redshifted and dimmed by the gravitational field. As you approach the event horizon, the light struggles more against gravity's pull, taking longer to climb out. Exactly at the event horizon, light aimed directly outward would remain frozen in place, neither advancing outward nor falling inward. Light aimed at any other angle would fall inward toward the singularity. Inside the event horizon, even light aimed directly outward falls inward, because all future directions lead to the singularity. The size of the event horizon scales with mass in a straightforward way. The Schwarzschild radius, derived by Carl Schwarzschild in 1916, gives the event horizon radius for a non-rotating black hole. The formula is simple: multiply the black hole's mass by 2 times Newton's gravitational constant, then divide by the speed of light squared. For a black hole of 1 solar mass, this produces a radius of about 3 kilometers. For 40 billion solar masses, the radius becomes about 690 astronomical units. The scaling is linear. Doubling the mass doubles the radius, because the event horizon is a feature of the gravitational field rather than a physical object that resists compression. Real black holes likely rotate, which modifies their structure in important ways. A rotating black hole, described by the Kerr metric found by Reuter in 1963, has 2 important surfaces rather than 1. The outer surface is the event horizon, which plays the same role as in the non-rotating case. Inside this lies the ergosphere, a region where spacetime itself rotates with the black hole, dragging everything along. An object in the ergosphere cannot remain stationary relative to distant stars, even if it fires rockets trying to do so. The rotating spacetime pulls everything in the direction of the black hole's rotation. The ergosphere exists because the black hole's rotation drags spacetime, an effect called frame dragging, which becomes extreme close to the event horizon. The largest black holes almost certainly rotate. Angular momentum is conserved as matter falls into a black hole, and since all infalling matter has some net angular momentum relative to the black hole's center, the black hole accumulates angular momentum and spins faster. There are theoretical limits to how fast a black hole can spin, determined by the point where adding more angular momentum would require the infalling matter to orbit faster than light, which is impossible. Real black holes probably spin at significant fractions of this maximum rate. Observations of accretion disk emissions and jets suggest many supermassive black holes rotate rapidly. Rotation affects the event horizon's size and shape. A maximally rotating black hole has an event horizon radius only half as large as a non-rotating black hole of the same mass. The horizon becomes oblate, bulging at the equator and flattened at the poles, though the deviation from spherical shape is small unless the spin rate is very high. For the largest black holes, even a factor of 2 difference in radius still leaves an enormous region enclosed by the event horizon. A rapidly rotating 40 billion solar mass black hole would have an event horizon radius of about 345 astronomical units, still far larger than our solar system. Falling through the event horizon of a supermassive black hole would be, paradoxically, and remarkable from the perspective of someone doing the falling. The equivalence principle, a cornerstone of general relativity, states that a freely falling observer experiences no local gravitational effects. In free fall, you are weightless, whether falling toward Earth or falling through a black hole's event horizon. The extreme curvature of spacetime exists, but its effects manifest only when comparing measurements at different locations. An astronaut falling through the event horizon of a supermassive black hole would notice nothing special at the moment of crossing because the curvature is spread over such a large region. That tidal forces remain weak. Tidal forces arise from differences in gravitational acceleration across an extended object. Your feet might be pulled slightly harder than your head if you fall feet first. For a stellar mass black hole, these tidal forces become tremendous at the event horizon, enough to tear apart any object. But tidal forces decrease as black holes get larger because the event horizon moves farther from the central singularity where curvature is most extreme. For the largest supermassive black holes, tidal forces at the event horizon are actually quite small, well within the tolerance of human tissue. An astronaut could survive crossing the event horizon, at least briefly, before the inevitable fall to the singularity. The view from inside the event horizon would be strange. Looking outward, the astronaut would see the entire external universe compressed into a shrinking circle of increasingly blue-shifted light. Light that started falling toward the black hole before the astronaut can still reach them, but this light gets compressed in both space and time. The external universe appears to speed up, with events occurring at an accelerated rate from the perspective of the infalling observer. Eventually, all the light from the universe's entire remaining history would rain down on the astronaut in a finite time before reaching the singularity. looking inward, toward the singularity, presents a view no one truly understands. General relativity predicts the singularity as a point where curvature becomes infinite, and the theory breaks down. Physical infinities usually signal that our mathematical description is incomplete rather than representing actual reality. Quantum mechanics must play a role at such extreme scales, but we lack a complete theory of quantum gravity to describe what really happens. The singularity might be a point of infinite density, or it might be a region where spacetime has a different structure we cannot currently describe, or it might be replaced by something entirely unexpected like a quantum foam of fluctuating geometry. What we can say with confidence is that the singularity is inevitable once you cross the event horizon. All paths forward in time lead there. The distance to the singularity is not measured in space but in time. For a non-rotating black hole, an observer falling from the event horizon reaches the singularity in a finite proper time, meaning time measured on their own clock. The calculation gives a time proportional to the black hole's mass. For a black hole of 40 billion solar masses, this time is roughly 11 hours. An astronaut falling through the event horizon has about 11 hours of subjective time before reaching the singularity, regardless of what trajectory they follow or what actions they take. They could fire rockets at full power, but this would only change their path through the interior spacetime, not prevent reaching the singularity. The event horizon is a one-way membrane, but one with a strange property. It is perfectly invisible from outside. Nothing marks its location in space. An observer hovering just outside the event horizon and looking at the horizon itself would see nothing. The horizon is not a physical surface. It's a surface in spacetime, a boundary between regions with different causal structure. Light from objects outside the horizon can reach this observer, but no light comes from the horizon itself or from the region inside. This invisibility means black holes really are black. They emit no light, and they absorb all light that falls in. The exception is Hawking radiation, a quantum mechanical effect predicted by Stephen Hawking in 1974. Quantum fluctuations near the event horizon can create particle-antiparticle pairs, with one particle falling into the black hole while the other escapes. This process causes black holes to emit thermal radiation with a temperature inversely proportional to mass. For supermassive black holes, this temperature is absurdly small, far colder than the cosmic microwave background that fills the universe. Hawking radiation from a 40 billion solar mass black hole would have a temperature of about 15 trillionths of a degree above absolute zero. The black hole gains energy by absorbing cosmic microwave background radiation far faster than it loses energy through Hawking radiation, so it grows rather than evaporating. The event horizon stands as a boundary where our everyday experience completely fails, where intuitions about cause and effect break down, where the structure of reality itself transforms into something alien. Yet for the largest black holes, this boundary encloses a volume comparable to small galaxies, a region where billions of stars could fit comfortably before reaching the edge of no return. Cosmic lighthouses, the largest black holes, spend most of their existence in darkness, dormant giants that have exhausted the gas supply in their immediate surroundings. But the most distant supermassive black holes we observe are anything but dark. They shine as quasars, the brightest persistent objects in the universe, outshining entire galaxies through the violent process of matter falling toward the event horizon. Understanding quasars reveals how supermassive black holes announce their presence across billions of light years and provides crucial evidence about how these objects grew in the early universe. Quasars were discovered by accident in the early 1960s when radio surveys identified powerful radio sources with peculiar properties. Optical telescopes viewing these positions found objects that looked like stars, simple points of light showing no extended structure. But spectra of these quasi-stellar radio sources, later shortened to quasars, showed emission lines at wavelengths that matched no known elements in laboratory studies. Martin Schmidt at Caltech solved the puzzle in 1963 when examining the spectrum of the quasar 3C273. The emission lines matched hydrogen, but shifted dramatically toward longer, redder wavelengths. The redshift indicated 3C273 was receding at 16% the speed of light, placing it roughly 2 billion light-years away according to Hubble's law connecting redshift to distance. This distance created an immediate problem. For 3C273 to appear as bright as it does in our telescopes despite being 2 billion light-years away, it must emit enormous energy, more than an entire galaxy of hundreds of billions of stars. Yet the object varied in brightness over months, or even weeks, which meant the emitting region could be no larger than light months, or light weeks across, far smaller than a galaxy. Nothing in conventional astrophysics could produce such enormous energy from such a compact region. The only viable explanation involved gravitational energy release from matter falling into a supermassive black hole. The mechanism works through conversion of gravitational potential energy into radiation. When matter falls toward a black hole, it speeds up, gaining kinetic energy extracted from the gravitational field. In isolation, this matter would simply cross the event horizon and disappear. But when multiple streams of infalling matter interact, they collide and dissipate kinetic energy as heat, forming an accretion disk where matter spirals gradually inward while heating to millions of degrees. Hot matter radiates, with the spectrum depending on temperature. The inner regions of an accretion disk around a supermassive black hole reach temperatures high enough to emit ultraviolet and X-ray radiation. The total energy output can reach enormous values because the conversion efficiency of mass to energy via accretion onto black holes is remarkably high. Einstein's equation E equals mc tells us that mass can be converted to energy, with the speed of light squared as the conversion factor. Nuclear fusion in stars converts roughly 1% of the mass into energy by combining hydrogen into helium. Matter falling into a black hole can convert 10% or more of its rest mass into radiation before crossing the event horizon. This factor of 10 advantage over fusion explains why quasars can outshine galaxies despite involving only the matter immediately near one central black hole, rather than the distributed nuclear reactions of billions of stars. The maximum luminosity a quasar can achieve connects to the Eddington limit mentioned earlier. Radiation exerts pressure on matter through interactions between photons and charged particles. As the quasar brightens, this radiation pressure pushes outward on the infalling gas, counteracting gravity's inward pull. The Eddington luminosity is the point where radiation pressure exactly balances gravitational attraction for a given mass. Above this luminosity, radiation pressure would exceed gravity and blow away the accreting matter, shutting off the quasar. This self-regulating mechanism means quasar luminosity correlates with black hole mass. More massive black holes can shine brighter before hitting the Eddington limit. The most luminous quasars observed shine with the light of tens of trillions of suns. These ultraluminous quasars require black holes weighing billions of solar masses to avoid exceeding the Eddington limit. When astronomers calculate the black hole mass needed to power observed quasar luminosities, they find supermassive black holes existed when the universe was less than 1 billion years old. These ancient behemoths pose the growth problem discussed earlier. How did they form and grow so large so quickly after the Big Bang? Quasars show strong evolution with cosmic time. They were most common when the universe was 2 to 3 billion years old. A period called the quasar epoch when roughly 1% of massive galaxies hosted actively feeding supermassive black hole. Bright enough to qualify as quasars. Before this epoch, the universe was younger and galaxies were still forming, so fewer massive black holes existed. After the quasar epoch, the rate of quasar activity declined dramatically. By the present day, only a tiny fraction of galaxies host quasars, and most supermassive black holes sit dormant, starved of fuel. This evolution reflects the cosmic history of gas availability and galaxy mergers. The largest black holes we know today were likely quasars in the past. Holmberg 15A's 40 billion solar mass black hole must have shone brilliantly as it accumulated mass through multiple galaxy mergers. Each merger would deliver fresh gas to the central black hole, triggering episodes of intense accretion and quasar activity. Between mergers, the black hole would fade as it consumed the available gas and its own feedback expelled or heated the remaining fuel. The long-term average duty cycle, the fraction of time a supermassive black hole spends as an active quasar, is estimated at perhaps 1 to 10% over cosmic history. Most of the time, these objects sit dark. Jets provide another spectacular manifestation of black hole activity. Some accreting black holes launch narrow beams of matter and energy that extend millions of light-years from the galactic center. These relativistic jets contain charged particles accelerated to nearly the speed of light, carrying tremendous energy far from the black hole. The launching mechanism involves magnetic fields threading the accretion disk and possibly the black hole's ergosphere. As the disk rotates, it twists and amplifies magnetic field lines, which can extract rotational energy from the black hole itself through a process called the Blandford's-Knight mechanism. The magnetic fields channel material into narrow beams aligned with the black hole's rotation axis, where the matter streams outward at relativistic speeds. When a jet points roughly toward Earth, relativistic effects cause the emission to appear dramatically brighter than it would if we viewed the jet from the side. The combination of matter moving toward us at nearly light speed creates a Doppler boost, making these blazars the brightest persistent electromagnetic sources in the universe. The variation in jet brightness depending on viewing angle explains why some quasars appear as powerful radio sources with jets, while others show up primarily in optical and X-ray surveys with no strong radio emission. The underlying objects are similar, but our perspective makes them appear different. Observations across the electromagnetic spectrum provide complementary information about quasars and active black holes. Radio observations detect synchrotron radiation from relativistic electrons spiraling in magnetic fields, tracing jets and large-scale radio lobes inflated by jets. Optical and ultraviolet observations measure the thermal emission from the accretion disk, with hotter inner regions producing shorter wavelengths. X-ray observations probe the innermost regions where the hottest gas exists and where high-energy processes like inverse Compton scattering boost photon energies. Infrared observations can penetrate dust that obscures optical light, revealing hidden quasars whose emission has been absorbed by surrounding dust and re-radiated at longer wavelengths. The spectrum of a quasar contains absorption and emission lines that encode detailed information about the physics of accretion. Broad emission lines with widths indicating velocities of thousands of kilometers per second arise from gas clouds orbiting close to the black hole in a region called the broad line region. These clouds move so fast that Doppler broadening smears the emission lines across a wide wavelength range. Narrower emission lines come from gas farther out, moving more slowly under the black hole's gravity. The ratios of different emission line strengths constrain the gas composition, temperature, and density. Absorption lines in quasar spectra sometimes indicate intervening material along the line of sight between the quasar and Earth. These absorption systems might be gas clouds in the quasar's host galaxy, gas in intervening galaxies, or diffuse intergalactic gas. By studying absorption lines at different redshifts corresponding to different distances from Earth, astronomers use quasars as backlights to probe the intervening universe. This technique reveals the distribution of matter throughout cosmic history and provides evidence for the existence and properties of intergalactic gas. The fuel supply for quasars comes from galactic-scale processes. Gas in the outer regions of galaxies has too much angular momentum to fall directly into the central black hole. Something must remove this angular momentum, allowing the gas to spiral inward. Galaxy mergers provide one mechanism. When two galaxies collide, gravitational interactions disturb the orderly orbits of gas and stars, redirecting some gas toward the galactic center. Gravitational instabilities in gas-rich disks can also drive gas inward through the formation of bars and spiral patterns that transport angular momentum outward while allowing mass to move inward. Once gas reaches the inner regions of a galaxy, it can form a reservoir that feeds the central black hole over extended periods. The feeding rate determines the quasar's brightness, and this rate can vary over time as the reservoir is replenished by inflows or depleted by accretion and feedback. Variability in quasar brightness, observed on timescales from days to years, reflects changes in the accretion rate or instabilities in the accretion flow. Some quasars have been observed to change dramatically in brightness over human timescales, fading from prominent quasars to faint or even disappearing from optical surveys, indicating the black hole's fuel supply was suddenly cut off. The study of quasars connects the extreme physics of black hole accretion to the large-scale evolution of galaxies and the universe. These cosmic lighthouses shine across billions of light-years, allowing us to study conditions in the early universe and trace how supermassive black holes grew to their present enormous sizes. The brightest quasars likely host some of the most massive black holes, though the uncertainty in mass measurements for extremely distant objects makes definitive rankings difficult. What remains clear is that the same physics governs accretion onto black holes whether they weigh millions or tens of billions of solar masses. The scale changes, but the fundamental processes remain the same. Galactic regulation. The relationship between supermassive black holes and their host galaxies represents one of the most significant discoveries in modern astrophysics. These objects, with size scales differing by factors of millions, influence each other's evolution through feedback mechanisms that shape galaxy structure and regulate star formation. The largest black holes sit at the centers of the most massive galaxies, and this correlation is not coincidental. It reflects a fundamental connection between black hole growth and galaxy evolution that operates throughout cosmic history. The in-sigma relation provides quantitative evidence for this connection. Discovered in the late 1990s through observations of nearby galaxies, this empirical relation connects the mass of a galaxy's central black hole to the velocity dispersion of stars in the galactic bulge. Velocity dispersion measures the spread of stellar velocities around the average motion, with higher dispersion indicating faster-moving stars. The relation shows that black hole mass increases as approximately the fourth power of velocity dispersion. A galaxy with twice the stellar velocity dispersion hosts a black hole 16 times more massive. This steep relation means small changes in galactic properties correspond to large changes in black hole mass. The remarkable aspect of this correlation is its tightness and consistency across different types of galaxies and a wide range of masses. Elliptical galaxies, spiral galaxies with prominent bulges, and compact bulges in smaller galaxies all follow approximately the same relation. The scatter around the best fit relation is relatively small, suggesting a physical process links these properties rather than the correlation arising by chance. Moreover, the relation holds from black holes of millions of solar masses up to the ultramassive black holes of tens of billions of solar masses, covering more than 4 orders of magnitude. The physical interpretation of the in-sigma relation involves feedback from the black hole regulating its own growth and affecting the entire galaxy. When a supermassive black hole accretes matter rapidly, it releases enormous energy through radiation and jets. This energy couples to the surrounding gas, heating it or driving powerful winds that sweep through the galaxy. Hot or expelled gas cannot collapse to form new stars, effectively shutting down star formation throughout the galaxy. The same process that heats and expels gas also removes the fuel supply for continued black hole growth, creating a self-regulating cycle. Simulations of galaxy formation demonstrate how feedback operates. Without black hole feedback, simulated galaxies grow to massive and to blue compared to observations. Too much gas cools and forms stars, creating galaxies dominated by young blue stars rather than the old red stellar populations observed in massive elliptical galaxies. When black hole feedback is included in the simulations, with appropriate prescriptions for how energy from accretion couples to surrounding gas, the simulated galaxies match observed properties much better. The feedback suppresses star formation in massive galaxies, explaining why the most massive galaxies contain mostly old stars despite sitting in regions with abundant gas. Different modes of feedback operate at different times. Quasar mode feedback, also called radiative mode, dominates during periods of rapid black hole growth when the accretion rate is high. The enormous luminosity of the quasar drives powerful winds that can expel gas from the entire galaxy. Evidence for such outflows appears in spectra showing blue-shifted absorption lines, indicating gas moving toward us at thousands of kilometers per second. The mass outflow rates in these quasar-driven winds can exceed the star formation rate, meaning the black hole removes gas faster than stars can form, effectively starving the galaxy. Radio mode feedback, also called maintenance mode, operates when the black hole accretes at low rates insufficient to power bright quasar but sufficient to launch jets. These jets inject energy into the hot gas surrounding the galaxy, preventing that gas from cooling and falling inward to form stars. X-ray observations of galaxy clusters reveal cavities in the hot intracluster gas where jets from the central galaxy's black hole have pushed the gas aside. Inflating bubbles that can be hundreds of thousands of light-years across. The energy required to create these structures reaches values equivalent to tens of millions of supernovae, far exceeding what stellar processes can provide. The balance between cooling and heating in the hot gas determines whether a galaxy can continue forming stars. In massive elliptical galaxies and galaxy clusters, hot gas contains substantial mass. If this gas could cool efficiently, it would collapse toward the galactic center, providing fuel for both star formation and black hole growth. Observations show that the cooling rates are much lower than expected, suggesting something prevents the gas from cooling. Radio mode feedback from the central black hole provides the heating mechanism, depositing energy into the gas at roughly the rate needed to offset cooling. The process creates a feedback loop. If the gas starts to cool and fall inward, the increased accretion onto the black hole strengthens the jets, which heat the gas and slow the cooling. This self-regulation maintains the balance. The timing of different feedback modes relates to galaxy evolution stages. Quasar mode dominates during major galaxy mergers when large amounts of gas funnel to the galactic center, triggering rapid black hole growth and powerful feedback that transforms the galaxy. After the merger, the gas supply depletes, the quasar fades, and the black hole enters radio mode where it maintains the galaxy in a state where star formation remains suppressed. This progression explains the observed evolution of galaxy properties with cosmic time and the transition from the quasar epoch to the present day where most supermassive black holes are dormant. The largest black holes show signs of particularly powerful past feedback. Giant elliptical galaxies at the centers of galaxy clusters, like Holmberg 15A, sit in environments where the accumulated mass in hot gas should be cooling and forming stars at high rates. Yet these galaxies form few if any new stars, indicating effective suppression of cooling. X-ray imaging reveals the signatures of repeated feedback episodes where jets inflated bubbles in the hot gas, and shock fronts propagating through the gas indicate energy injection events. The total energy deposited by these feedback episodes over billions of years can exceed the gravitational binding energy of the hot gas, demonstrating that black hole feedback is powerful enough to significantly affect galaxy-scale properties. Stellar populations in massive elliptical galaxies provide additional evidence for the role of feedback. These galaxies contain primarily old stars with ages of 10 billion years or more, indicating star formation ceased long ago. The termination of star formation correlates with the time when the galaxies assembled most of their mass through mergers, which also corresponds to when their central black holes grew rapidly. The implication is that black hole feedback ended star formation, leaving behind the old stellar populations we observe today. The connection between black holes and galaxies extends to the formation of structure throughout the universe. Dark matter provides the gravitational scaffolding that holds galaxies together, but bright matter, which includes gas and stars, responds to additional physics including cooling, star formation, and feedback. The distribution of galaxies by mass shows a characteristic shape with relatively few very massive galaxies. This shape results partly from black hole feedback suppressing the formation of the most massive galaxies. Without feedback, theories predict more massive galaxies should exist than are actually observed. Feedback also affects the properties of the intergalactic medium, the diffuse gas between galaxies. Energy from quasars and jets can heat this gas or enrich it with heavy elements created in stars and expelled during feedback episodes. Observations of absorption lines in quasar spectra provide evidence for metal-enriched gas far from galaxies, indicating past feedback transported material over enormous distances. The thermal history of the intergalactic medium connects to the integrated energy input from all sources of feedback throughout cosmic history. Alternatives to black hole feedback struggle to explain all observations. Supernova feedback from star formation can heat gas and drive winds, but supernova energy is insufficient to expel gas from the deep gravitational potential wells of the most massive galaxies. Cosmic rays, high-energy particles accelerated in supernova remnants and other sites, might contribute to heating and pressure support, but they seem unable to fully suppress cooling in massive systems. Black hole feedback, with its ability to tap the enormous gravitational energy reservoir of infalling matter and deliver that energy over large volumes through jets and winds, provides the most viable explanation for the observed properties of massive galaxies. The regulatory role of supermassive black holes has profound implications. These objects, despite containing less than 1% of their host galaxy's mass, control the fate of the remaining 99%. The star formation history of the galaxy, the chemical composition of its stars and gas, and ultimately the galaxy's appearance and evolution all depend on feedback from the central black hole. In the most massive galaxies, which host the largest black holes, this feedback has been so effective that it essentially ended the galaxy's evolution, leaving behind a static collection of old stars with little ongoing activity. Understanding black hole feedback requires combining observations across many wavelengths, theoretical modeling of feedback physics, and sophisticated simulations that follow galaxy evolution over cosmic time. Recent progress has improved our understanding of how energy couples to gas and what determines the efficiency of feedback, but many details remain uncertain. The challenge lies in connecting processes operating at vastly different scales. From the event horizon of the black hole measured in light hours to the galaxy measured in tens of thousands of light years. Yet the observational evidence for strong connections between these scales is undeniable, and the largest black holes provide the most dramatic examples of feedback shaping galactic structure. Formation mysteries. The origin of the first supermassive black holes remains one of the deepest puzzles in astrophysics. These objects existed when the universe was less than 1 billion years old, yet their formation requires mechanisms that operate faster than the standard pathways we understand today. The puzzle intensifies when considering the largest black holes, which must have grown even more rapidly or started from more massive seeds than typical supermassive black holes. Solving this mystery requires looking back to the early universe when conditions differed dramatically from what we observe in the local cosmos. The standard pathway for black hole formation involves stellar collapse. Massive stars with initial masses exceeding about 20 times the Sun's mass exhaust their nuclear fuel and collapse under their own gravity, forming stellar mass black holes weighing 10 to perhaps 100 solar masses. This process has operated throughout cosmic history, creating a population of stellar mass black holes distributed throughout galaxies. But starting from 100 solar masses and growing to billions of solar masses in less than 1 billion years requires accretion rates that challenge theoretical limits. The Eddington limit constrains how fast black holes can grow by accretion. At the Eddington luminosity, radiation pressure from accreted matter exactly balances gravitational attraction, preventing more matter from falling in. The corresponding accretion rate, called the Eddington rate, depends on black hole mass. More massive black holes can accrete faster in absolute terms, but the relative growth rate decreases. A black hole accreting at the Eddington rate increases its mass exponentially with an e-folding time of about 45 million years. Starting from 100 solar masses and growing at this rate for 1 billion years would produce a black hole of roughly 10 billion solar masses, which seems adequate to explain observations. However, this calculation assumes several optimistic conditions. The black hole must form very early, within the first few 100 million years after the Big Bang. It must have a continuous supply of gas to accrete at the Eddington rate without interruption for the entire billion-year period. And it must convert gas into black hole mass with perfect efficiency, with no mass loss through winds or jets. Real systems violate all these assumptions. Black holes accrete in episodes separated by periods of low activity. Feedback from accretion can expel gas, reducing or eliminating the fuel supply. And the conversion efficiency is less than perfect, with some accreting matter being ejected in winds or jets rather than crossing the event horizon. These complications motivate alternative formation scenarios that start with more massive seeds. If the first black holes could form with masses of 10,000 or even 1 million solar masses, they would have a head start on growth that makes reaching billions of solar masses by early times more plausible. Several theoretical mechanisms might produce such massive seeds, though each faces challenges in satisfying all necessary conditions. Direct collapse black holes represent one possibility. Under specific conditions in the early universe, a gas cloud might collapse directly into a massive black hole without fragmenting into stars first. The key requirement is preventing the formation of molecular hydrogen, which normally cools gas efficiently and allows fragmentation into star-sized clumps. Intense ultraviolet radiation from nearby sources can dissociate molecular hydrogen faster than it forms, keeping the gas hot. Hot gas resists fragmentation, allowing the entire cloud to collapse together into a black hole of 10,000 to 100,000 solar masses. The challenge for direct collapse involves creating the necessary conditions. The ultraviolet radiation must be strong enough to prevent molecular hydrogen formation, but not so strong that it heats the gas enough to prevent collapse altogether. The gas must be pristine, or nearly so, containing only hydrogen and helium without heavier elements that provide additional cooling pathways. And the process must occur in halos of dark matter that are massive enough to hold the gas gravitationally, but not so massive that stars have already formed. Simulations suggest these conditions might be satisfied in rare special regions of the early universe, potentially creating a population of direct collapse black holes that serve as seeds for supermassive black hole growth. Supermassive stars provide another pathway to massive seeds. In the dense stellar clusters that might form in the first galaxies, stellar collisions could be common. When stars collide, they merge into larger stars, and a runaway process might create a supermassive star weighing thousands of solar masses. Such a star would be unstable to pulsations and would likely collapse into a black hole of comparable mass after a relatively short lifetime of perhaps 1 million years. The resulting intermediate mass black hole could then grow through continued accretion and collisions to become a supermassive black hole. The difficulty with this scenario involves forming the initial dense cluster and maintaining conditions where collisions dominate over stellar evolution. Stars must be packed closely enough that collisions occur frequently, requiring stellar densities far higher than observed in any present-day cluster. Such extreme densities might have existed in the first dark matter halos where gas collapsed to very high densities before forming stars. But verifying this requires detailed simulations of early star formation, including the complex physics of stellar collisions and mergers. Primordial black holes offer a more exotic possibility. In the very early universe, quantum fluctuations during cosmic inflation might have created regions of enhanced density that collapsed into black holes when the universe was less than 1 second old. The mass spectrum of primordial black holes depends on details of the inflationary model and the nature of quantum fluctuations. Most models predict primordial black holes would be quite small, but some variations allow for larger masses. If primordial black holes could form with masses of thousands or millions of solar masses, they would provide ready-made seeds for supermassive black hole growth. The main issue with primordial black holes as seeds is the lack of observational evidence for their existence at any mass. Searches for primordial black holes through gravitational lensing, dynamical effects on stellar systems, and gravitational wave signals have constrained the possible abundance and mass ranges. Current constraints suggest primordial black holes cannot make up the majority of dark matter across most mass ranges, though windows remain open where they might exist in smaller numbers. Using them to explain supermassive black hole formation requires both that they exist and that they form preferentially in locations that became the centers of early galaxies. A fourth possibility involves black hole mergers as a rapid growth mechanism. If black holes can find each other and merge efficiently in the early universe, the resulting black hole grows in discrete jumps rather than smooth accretion. A series of mergers could potentially overcome the slow growth rate imposed by Eddington limited accretion. The challenge here is efficiency. Black holes must sink to the centers of their host dark matter halos through dynamical friction, and multiple black holes must find each other and merge before they exhaust the local supply of gas and stars that mediates dynamical friction. Observations provide crucial constraints on formation scenarios. The discovery of quasars at redshifts greater than 7, corresponding to when the universe was less than 800 million years old, demonstrates that billion solar mass black holes existed at these early times. The spectra of these quasars show evidence for metal enrichment, indicating previous generations of star formation occurred before the quasar became active. This timeline is extremely tight, requiring both the formation of stars and the growth of supermassive black holes within the first several hundred million years after the Big Bang. The James Webb Space Telescope has begun detecting even earlier black holes, potentially pushing the existence of supermassive black holes to even younger cosmic ages. Each new discovery that pushes black hole formation earlier in cosmic history tightens the constraints on formation mechanisms and makes exotic scenarios like direct collapse or massive primordial seeds more attractive relative to scenarios that rely on stellar mass seeds and standard accretion. The largest black holes we observe today, like the one in Holmberg 15A, might represent the endpoints of different formation and growth pathways. A black hole that started early, grew rapidly through super-Eddington accretion during its early phases, and then experienced multiple major mergers as its host galaxy grew through accretion of smaller galaxies might reach masses of tens of billions of solar masses. Alternatively, several large seed black holes forming in different proto-galaxies that later merged could combine to create today's most massive black holes. Distinguishing between these possibilities requires better observations of black holes at intermediate cosmic times and improved theoretical modeling of all the relevant physical processes. The formation environment matters as well. The early universe was denser, and structures formed more rapidly. Dark matter halos collapsed earlier and reached higher densities than similar mass halos today. Gas had not yet been enriched with heavy elements from stellar nucleosynthesis, changing its cooling and fragmentation properties. These differences mean formation mechanisms that operate efficiently in the early universe might not work at later times, explaining why we observe supermassive black holes forming early, but not seeing equivalent formation today. Feedback plays a role in formation as well. A growing black hole heats and ionizes surrounding gas, changing the conditions for continued accretion. Once a black hole grows large enough that its feedback becomes powerful, it might self-regulate its growth rate or even shut off accretion entirely for a period. Understanding how feedback operates at early times when black holes are still growing requires modeling the interplay between accretion, radiation, jets, and the response of surrounding gas in the high-density environments of early galaxies. The mystery of supermassive black hole formation connects to broader questions about how the first structures formed in the universe, how the first stars and galaxies came into being, and how the universe transitioned from the smooth state shortly after the Big Bang to the rich structure we observe today. Solving this mystery requires pushing observational capabilities to detect and characterize the earliest black holes and developing theoretical frameworks that capture all relevant physics across an enormous range of scales. The largest black holes, requiring the most extreme growth, provide the most stringent tests of our understanding. The existence of ultramassive black holes raises an inevitable question: is there a maximum size, and have we already found black holes approaching this limit? Physical processes suggest several mechanisms that might cap black hole growth, preventing arbitrarily large black holes from forming. Understanding these limits requires examining the interplay between black hole accretion, feedback effects on the surrounding environment, and the long-term evolution of galaxies. The fundamental limit on black hole growth comes from the finite amount of matter available. A black hole can only grow as large as the mass it can capture from its surroundings. The total mass available includes the gas content of the host galaxy, the stellar mass that might eventually feed the black hole, and material that might fall in during galaxy mergers. For the most massive galaxies, the stellar mass reaches roughly 1 trillion solar masses. If even a few % of this mass eventually falls into the central black hole, masses of tens of billions of solar masses become possible, consistent with the largest black holes observed. However, most matter in a galaxy will never reach the central black hole. Stars orbit the galaxy under the combined gravitational influence of dark matter stars and gas, following stable orbits that keep them at large radii. Gas can lose angular momentum through viscosity, magnetic fields, or gravitational torques, allowing it to spiral inward, but these processes are inefficient. The time scale for gas at the outskirts of a galaxy to spiral into the center exceeds the age of the universe unless some mechanism actively transports it inward. Galaxy mergers provide such a mechanism, but even mergers deliver only a fraction of the total galactic mass to the central regions. Feedback from black hole accretion provides a more stringent limit than the total available mass. As discussed earlier, energy released during accretion can heat or expel gas from the galaxy, removing the black hole's fuel supply. The efficiency of feedback depends on how effectively energy couples to gas. If 10% of the accreted mass converts to energy, and 10% of that energy couples to the surrounding gas, then 1% of the accretion energy heats the gas. For a black hole of 40 billion solar masses growing at the Eddington rate, the energy output reaches staggering values, approximately 10 to the 47th watts. Even a small fraction of this energy can heat the entire galaxy's gas reservoir, suppressing further accretion. The balance between black hole gravity and feedback creates a self-regulated equilibrium. When the black hole is small relative to the galaxy, its gravitational influence is limited and feedback is weak, allowing rapid growth. As the black hole grows, its gravitational pull strengthens, potentially attracting more gas, but its feedback also strengthens, heating gas and driving winds that remove fuel. Eventually, feedback becomes strong enough to balance or exceed the gas supply, halting further significant growth. The mass where this balance occurs depends on galaxy properties, explaining why more massive galaxies with deeper gravitational potential wells, where gas is harder to expel, host more massive black holes. Observational evidence supports the idea that the most massive black holes have reached an equilibrium with their environments. Giant elliptical galaxies show little ongoing star formation and little cold gas, indicating their gas has been heated or expelled. The central black holes in these galaxies accrete at very low rates, far below the Eddington limit, suggesting they have exhausted their fuel supply. The radio jets these black holes produce inject energy into the surrounding hot gas at roughly the rate needed to prevent cooling, maintaining the equilibrium. This picture suggests the largest black holes have effectively stopped growing except through occasional mergers that deliver new gas or combine black holes directly. Dynamical processes provide additional constraints on black hole size. As black holes grow through mergers, the final black hole recoils due to conservation of momentum if the merging black holes have different masses or spins. Gravitational waves carry away momentum asymmetrically, imparting a kick velocity to the remnant black hole. For comparable mass mergers with favorable spin configurations, kick velocities can reach thousands of kilometers per second. If this velocity exceeds the escape velocity from the galaxy, the black hole can be ejected, carrying its mass away and preventing it from contributing to further growth of the galactic center black hole. Escape velocity depends on galaxy mass, with more massive galaxies having deeper potential wells and higher escape velocities. The most massive galaxies have escape velocities from their central regions of roughly 1,000 to 2,000 kilometers per second. Black hole merger kicks typically fall below this value, but extreme configurations can produce larger kicks. The possibility of black hole ejection might limit how large black holes can grow through mergers, though the actual importance of this effect remains debated. Simulations suggest that black holes in the most massive galaxies are unlikely to be ejected even in extreme merger configurations. But smaller galaxies might lose their central black holes through merger kicks. Another limit arises from the structure of dark matter halos. Galaxies sit within extended halos of dark matter that provide most of the gravitational mass holding the galaxy together. The dark matter halo has a characteristic mass that grows over cosmic time as structure forms hierarchically, with smaller halos merging to form larger ones. The most massive dark matter halos in the present-day universe weigh roughly 10 to the 15 solar masses. The baryonic matter that forms stars and feeds black holes represents only about 15% of the total mass, with the rest being dark matter. This sets an upper limit on how much matter is available to form galaxies and feed black holes within any given halo. The relationship between dark matter halo mass and black hole mass suggests black holes in the most massive halos should weigh tens of billions of solar masses, consistent with observations. If the scaling observed in nearby galaxies continues to the most massive systems, and if these systems have had sufficient time for their black holes to grow to equilibrium with the halo, then we might expect maximum black hole masses around 100 billion solar masses. Current observations suggest the largest black holes reach about 40 to perhaps 100 billion solar masses depending on measurement uncertainties, indicating we may be observing black holes near the practical maximum set by available matter and feedback. Theoretical predictions for the maximum black hole mass vary depending on assumptions about formation history and growth mechanisms. Conservative models assuming Eddington limited growth predict maximum masses of a few billion solar masses, which is well below the largest observed black holes, suggesting super Eddington accretion occurred at some point. Models including super Eddington phases and multiple mergers can produce black holes of 100 billion solar masses or more, potentially exceeding current observations. The uncertainty reflects our incomplete understanding of how efficiently black holes grow under different conditions. The cosmic expansion also sets a limit on how large black holes can grow. As the universe expands and the dark energy component becomes dominant, the formation of new structures slows and eventually ceases. Gravitationally bound systems like galaxies continue to exist, but they stop accreting material from the surrounding universe. The formation of new galaxy clusters effectively ended a few billion years ago, and individual galaxies are becoming increasingly isolated as cosmic expansion accelerates. This means black holes have a finite time to grow through mergers and accretion before their fuel supply is permanently cut off by cosmic expansion. Looking forward billions of years, the universe will continue expanding, and galaxies will become more isolated. Within galaxy clusters, galaxies will continue to merge over tens to hundreds of billions of years, potentially allowing black holes to grow somewhat larger through mergers. The ultimate fate involves all galaxies in a cluster merging into a single giant elliptical galaxy containing a single ultramassive black hole that accumulated the mass of all the original central black holes. This process could create black holes of hundreds of billions of solar masses in rare cases, but the timescales involved far exceed the current age of the universe. On even longer timescales, if black holes are truly stable, they will outlive stars, planets, and all other structures through Hawking evaporation. Small black holes evaporate faster, so stellar mass black holes will evaporate in 10 to the 67 years, far longer than the current age of the universe but finite nonetheless. Supermassive black holes will persist much longer, with evaporation timescales scaling as the cube of the mass. A 40 billion solar mass black hole will evaporate in roughly 10 to the 99 years, an incomprehensibly long time but still finite. Eventually, even the largest black holes will disappear, leaving behind nothing but photons and perhaps neutrinos in an exponentially expanding universe approaching absolute cold. The question of whether we've found the largest possible black hole remains open. Measurements of the most massive black holes carry substantial uncertainties, and discoveries of even larger examples remain possible as surveys improve. The distinction between the largest known black hole and the largest possible black hole reflects our incomplete census of the universe. We have surveyed only a tiny fraction of all galaxies in detail sufficient to detect and weigh their central black holes. In the vast volume of the observable universe, larger examples might exist in rare systems we haven't yet studied carefully. What we can say with confidence is that black holes larger than a few hundred billion solar masses seem unlikely based on current theoretical understanding of how they form and grow. Feedback effects appear strong enough to prevent larger masses from accumulating, and the finite age of the universe limits how much growth can occur. The largest black holes we observe today likely formed through a combination of early rapid growth and multiple major mergers throughout cosmic history. They represent the extreme end of black hole mass distribution, rare objects that required special conditions to form and grow. Whether significantly larger black holes exist remains an open question that future observations will address. The existence of ultramassive black holes has profound implications for our understanding of structure formation, galaxy evolution, and the nature of the universe itself. These objects serve as probes of physical processes operating under extreme conditions and as markers of how the universe evolved from the nearly smooth state shortly after the Big Bang to the rich structure we observe today. Examining the cosmic implications of the largest black holes reveals connections spanning from the event horizon to the observable universe itself. Black holes test general relativity in regimes where gravity becomes the dominant force. Einstein's theory has passed every experimental test so far, from the perihelion precession of Mercury to the detection of gravitational waves from merging black holes. But these tests mostly probe relatively weak gravitational fields where spacetime curvature remains small. Near the event horizon of a supermassive black hole, space-time curvature becomes extreme, providing the strongest possible test of general relativity short of observing the singularity itself. So far, observations remain consistent with Einstein's predictions, even in these extreme environments. The Event Horizon Telescope's imaging of M87's black hole provided visual confirmation of general relativity's predictions for what a black hole should look like. The dark central shadow surrounded by a bright ring of emission matched theoretical expectations based on ray tracing calculations through curved spacetime. The size of the shadow depends on the black hole's mass and distance, and the measured size agreed with the independently determined mass from stellar dynamics. Extensions of this technique to larger or more distant black holes, including potentially the largest known black holes, would further test whether general relativity remains valid at the largest scales. Gravitational waves from supermassive black hole mergers will provide complementary tests. The LIGO and Virgo detectors observe stellar mass black hole mergers, but their sensitivity peaks at frequencies too high to detect supermassive black hole mergers. Those mergers produce gravitational waves with periods of months to years, requiring space-based detectors or pulsar timing arrays. The Laser Interferometer space antenna, planned for launch in the 2030s, will target this frequency range, potentially detecting dozens of supermassive black hole mergers per year. Pulsar timing arrays, which detect gravitational waves by monitoring the precise arrival times of pulses from millisecond pulsars, have recently reported evidence for a gravitational wave background likely produced by many supermassive black hole mergers throughout the universe.